Madame et Monsieur, bonjour. That's all I can say. So, ladies and gentlemen, good afternoon. I'm very pleased to be here. I thank very much the organizer for this very nice opportunity and this very nice place. Actually, it's my second time that I enjoy to visit Institut Henri Poincaré, and it's a pleasure for me to talk about something new that we have done in the last, say, recent time, 2 years ago. Maybe I have to warn you that I'm I'm a mathematician, so I would put more emphasis on mathematical issues, and maybe I'm not so good in explaining the physics that I'm going to talk about, but I hope we can even afterwards discuss details if you want. So the topic of my talk is about controlling multi-particle systems, and in this sense I would like to say you have to think of a molecule, and in this molecule of the electrons in this molecule, or any other system with electrons that is confined by some potential. So maybe in these talks I haven't seen very much the space coordinate, but in this case the space coordinate plays a very big role. In fact, the dimensionality is the main issue, the dimensionality of the problem, and there is a fantastic way that has been found to overturn this problem that is as old as I am. I'm 53 years old, and in fact it was in 1965 that Kohn and Sham wrote their famous equations that drastically reduce the problem of dimensionality, and I would like to explain you what is the idea behind it. So the beginning of this talk is, as far as I can do, is to explain you what is density functional theory, and then how we thought to use this to design a control strategy for these multi-particle systems. In this case, I will always think of electrons. So as you all well know, the starting point is, let's say in the Schrödinger picture, is the Schrödinger equation. The Schrödinger equation we all will know. But this Schrödinger equation, if you have multi-particles, means that the Hamiltonian is representing all momenta or all kinetic energies of all electrons. So you have to think of, say, Laplacian operator for any of the electrons you have. And the wave function is a function of the coordinates of all the particles. So we are talking about n electrons. Each electron is in R3, so in a room. So we have 3 times n coordinates. So this is a function which is a very high dimensional, and it is essentially, let's say, impossible to handle it beyond some small number of n. So anyway, this is the original discussion we have, is to consider this Schrödinger equation and to put on the same side to put the idea of density function theory that will drastically reduce this dimensionality problem. So imagine, just to make things a little bit easier, as I said, imagine a molecule with nuclei and electrons. Let's just think of the molecule water, no? This is Mickey Mouse. So since nuclei are much heavier than electrons, then there is a famous approximation to make to reduce dimensionality of the problem, which is due to Born and Oppenheimer. In fact, the idea is to consider the nuclei of this molecule as fixed, generating a confining potential for the electrons, but they will not be described by the Schrödinger equation, will be considered as just an external potential. So in this case, we already have reduced the problem. So it is in fact about model reduction. We have reduced the model to the coordinates of the electrons alone. But as you see, if we just take the water molecule, which is a small molecule, with, with just 10 electrons, then you already have a very big problem. Because if you imagine to make a numerical simulation of this molecule, just take for each space coordinate, let's say 40 points in a Fourier space or a physical space, and you make, you compute the total number of these points, then you get to 10 to the power 48. And someone said me that this is the number of atoms in the Earth. So if you want, you need a computer which is essentially the Earth to represent this molecule. So this is, let's say, the limit we have. And this point comes from the fact that we want to describe the physics by the wave function, which is a high dimensional. But in fact, this is not necessary because many quantities that we want to measure or represent can be done through the density matrix operator. And the density matrix operator that you all use, I've seen a lot of times in these talks the Liouville for Neumann equation. If you think of it in the infinite dimensional space, like in this case, so the point is to define this operator, which we call density matrix or density operator, just defined in this way. This formulation here, you see, is the integration on n-1 coordinates. Remember that electrons are all equal up to the spin, and the antisymmetry here is a product of psi. So this is the density matrix in general for our Schrödinger problem. In particular, if you consider this operator, say the trace, then you get the electronic density, which is now, from one point of view, is a material quantity. It's really the density of electrons. In fact, if you integrate to it, then you would like to recover the number of electrons that you have. On the other hand, you can also think of the classical quantum mechanical interpretation by Bohr, and then it is the probability to find some electron in some place. Okay, so it's a probability density function. In both cases, what you notice is that this function depends only on 3 coordinates and not 3 times n coordinates. So it's, we have in the usual space where we live. And the point now is that if you think of quantum mechanics and of what we actually want to measure and predict, then we think of observables, and these are average quantities that if you use the wave function are written in this way. But in fact, if you have operators that are done for n particles as all equal sum of these operators, like kinetic energy or some potential, then you realize that this expectation value is in fact the trace of the product of the observable operator and the density operator. So it seems that we have a completely different picture, which is very low dimensional in comparison to the standard, to the original Schrödinger model. And this is the starting point of density functional theory. This fact was already recognized by Thomas and Fermi in 1927. So it is almost 1 century ago. And even if the theory of Thomas and Fermi, who recovered this theory independently, is affected by many errors, it was not accurate and so on, the idea was there. The idea was to describe, to use not the picture of Schrödinger. In fact, in that time the equation of Schrödinger was proposed, but to use the density matrix. And this idea was like doing fermentation, like a good Bordeaux wine, for a long time, until Hohenberg and Kohn in 1964 started to rigorously, or say more accurately, investigate the possibility to describe a quantum model by this density. And the first, say, theoretical approaches by Hohenberg and Kohn, I will discuss this later. And what makes the breakthrough was the equation of Kohn Sham that gave you a constructive way to have this density without solving the Schrödinger equation. So this is the path, the historical path we had. Then even if I would say the theory of density function theory is still under development, there are many points where we need to make better. There are important contributions, theoretical contribution by Levy. Actually, I forgot to write here, Levy and Lieb essentially in the same time. Especially Levy made a lot of consideration from convex analysis to show that it is possible to construct a functional which is convex and has a minima, which is the ground energy. And later, I would like to introduce you to the time-dependent density function theory, which is more recent. And in this case, the idea is that we don't want only to describe the ground state. We would like to make a model of the time evolution in transient phenomena. And this is essential for me, for us, to make control, because control must depend on time. You want to change energy of your system, do something. So let me explain you the essential idea. So essentially, first of all, think of the mapping that for us is all obvious. If you give a potential, you compute the eigenvalue problem for the Schrödinger equation, and you get a wave function, which is the eigenstate. If you take the lowest energy, the corresponding eigenstate is your ground state. So you already can make a lot of prediction about the energy of your system in a ground state. So this is a mapping, between potential and wave. The other mapping I've already described is that if you give me the wave function, then you make this integral and you get the density matrix. So we have two mappings, and the problem is now, what is the concatenation of these two? I mean, if I give you a potential, you compute the wave function, and if you have the wave function, you compute the density. So the question is, can we invert this map? If you see a density, is this density uniquely determined by a potential? Is a one-to-one map? So that if this is true, then I can think of inventing a new potential that gives me the same density in another system. So this is the starting idea. And to show you this, I don't know, did I jump some space? Yeah. So to show this, let me put you some functional spaces so that we know where we are and where we go, yeah? Because these mappings are not always well defined in any functional space. This is obvious, no? So the first is to see the functional space of the wave function. If you see a weak formulation of the Schrödinger equation, then you immediately see, because there is a second order operator, that your functional space must be in H1 in space. So you have the psi function. I don't know if you see, yes, the psi function is in H1. And this is omega n. So suppose we are in a bounded domain, and this is a Cartesian product of n times this domain, because there are n particles, and they have values on C. So we have a complex Hilbert space with the usual normalization. The other space we should discuss is the space where the density is, okay? So think of this integral. And because you want that the integral of the density is the number of particles, so you must be in L1. You must be integrable in L1. And moreover, it turns out that to have a bounded kinetic energy, also the square root of rho must be in H1. So one way to guarantee these two properties is to take a subset of the space L1, L3. In this case, you guarantee that the integral of rho is n, that the potential energy is bounded. I mean, this is a number, it's not infinite. And moreover, you can start asking which potentials are allowed that give me a density that has these properties. So the first property is that if I take the potential be bounded, then rho is in L1, so it's fine. Moreover, if rho is in L3, so this part here, which comes from this energy estimate, then I have that V can be in L3 divided by 2 by order inequality. So we can say that we can take all potentials that are composition of functions in L infinity and L3 half. So this is the norm we have. Okay? So this is essential because it says that you cannot take potentials that go in infinite forever. Let's say the harmonic potential. You cannot take it if you are in a bounded domain. But this is essentially, it's obvious, even if you write this every day. And, but you can take the Coulomb potential because you are in this space. Okay? So, let's remember again, we have free space. The space of wave functions, the space of density, the space of potentials. And now let's ask us if this mapping between potential, wave function, density can be inverted. Well, in generally not, if you are in these spaces, in the general setting I said. But if you go to a space where it's guaranteed that the potential has some ground states, then it is actually almost possible up to power sets. But let's make the discussion more clear, just considering the last line. So if we assume that the potential has a non-degenerate ground state, then this mapping between potentials, wave functions, and density is bijective. So I can go, if you give the density, you can go back to the potential. Okay? So this is what is about these two maps I'm discussing. This is essential to define the density functional theory. And, in fact, it was Hohenberg and Kohn, as I said, in 1964, who actually said that this is a bijection, at least if you are working with potential, you assume that this potential have a non-degenerate ground state. Actually, this has been extended to potentials that allow more so degenerate ground states. So this is the theory also of Lieb and Levy and so on, but I will not discuss this. The other point is that, in fact, we have a variational principle. So the energy, you have a functional that if you minimize this with the function density, the solution of this variational problem is in fact the ground state density. So it is the physical density that you wanted to have. The problem in this framework is that still we have to compute the Schrödinger equation because I have to construct a map. And so this is where the revolution comes due to Kohn and Sham. So Kohn won the Nobel Prize for this. No? The idea is that, in fact, we can think of another model, an alternative model. So here we have a 3 n-dimensional linear Schrödinger equation. The idea was, okay, then we take n-coupled 3-dimensional nonlinear Schrödinger equations where the coupling is such that the corresponding density is the same of the original Schrödinger equation. This magic works. Essentially works because we have proven that we have this bijective map between potentials and densities. So the idea of Kohn and Sham was that, first of all, to remember that if you have n interacting electrons, okay, so you have this the wave function with n coordinates, then you can think that you may have a coupled system of Schrödinger equation, each with some Ci with only 3-dimensional coordinate, and then make the Slater determinant so you get the antisymmetry you want, and construct your wave function. And this is the best, the most beautiful model reduction I know. No? This is a real model reduction. No? It's not a surrogate. Anyway, so we go from n-coupled three-dimensional nonlinear Schrödinger equation that give the same density of three n-dimensional linear Schrödinger equation. Okay, so let's see how it can work. Yeah. So imagine at the beginning the n-dimensional Schrödinger equation. So this here is actually n Laplacian, and you have an external potential that can include your control function, can include the external potential, and then you have interaction potential because we have electrons, so we have some Coulomb repulsion, no? So other particle-particle potential. Okay, so this is the density for this problem. But now the idea of Kohn Sham is, this is DFT, this is no time dependent. The idea is to add a potential that links all these Schrödinger equations. So we have actually here, this is a three-dimensional Laplacian. And you have there's a similar eigenvalue problem where the rho is now just the square of all the psi. Okay? So this is a great change in complexity of the problem. No? And in fact, it was Kohn and Hohenberg, and then Sham, then Levy, Lieb, etc., that proved that this rho is exactly this rho. At least it can be exactly if we are able to say what is the potential VKS. I wrote this as Kohn Sham. No? If we are able to find this potential here. And this is the issue, finding this potential. So this potential should contain the particle-particle interaction, in this case the Coulomb interaction. And for this there is already a nice line of studies started by R3, who proposed the R3 potential. This is like a mean field approach to looking at one electron in a cloud of all other electrons. Okay, so this is the R3 potential here. So you see we have the Coulomb structure. And then you need something more, because in the R3 potential there is no encoding of the Pauli principle. There is no exclusion principle. So this is the idea of the next potential. This is this one. This is the exchange potential. They should be such that you get the solution if you have this Pauli principle. And then there is a correction of the correction, this VC, which is a correlation potential, that we have to find out. Okay? So you know it works, but you don't know exactly how it works. So if you look at the literature about density function theory, there are many, many works that try to refine the construction, especially of this last part, this correction, yeah, which is not known analytically. Anyway, so let me say how we do this. So the first, the R3 potential is clear. The exchange potential that has to encode the Pauli's exclusion principle is a functional that it is already known. It goes like the n root of rho. N is the dimension of space. So I usually think of three-dimensional. I'll explain you why later. And for our mathematical issue, because we wanted to prove existence of solutions, existence of optimal controls, regularity, this is not enough, because this is unbounded. Right? Rho can be big in point-wise. So we put a cutoff, and to doing this in a way that makes everybody happy, since this is a non-relativistic quantum mechanics, we just choose R, this is the geometric distance R, which makes the cutoff through this polynomial as the Schwarzschild radius. So construct a black hole with the mass of an electron, then there is a nice formula by Karl Schwarzschild that tells you the radius is this. So we assume that if you come to this radius, then it cannot be non-relativistic anymore, no? So so in this, the referee was actually happy, no? Because we didn't specify before. Anyway, so the other important first condition is that this exchange potential is continuously differentiable and globally bounded. This is why we use this polynomial to get some differentiability properties. Okay, the Lada potential, the correction one, is not known analytically, but there are a lot of simulations with Monte Carlo to try to get the shape of it. And all that are known are actually of this form. They are 0 at 0 and have some convex structure. Okay? The quantity is say 1% of the exchange potential. It's very small, but this is essential in simulation. I should emphasize that the density functional theory is used every day by our colleagues in the chemistry department here and everywhere in the world, but also by physicists everywhere to make a very accurate simulation for molecules. So it is something which is used every day. And then it comes to the time. Then I would like to put the time in these problems. This is a more recent development. It's due to Runge-Gross, so essentially 20 years after the density function theory. The idea is now to have the possibility to model these multiparticles in transient regime, so where you have time, you need the time. And Runge and Gross started this work by, say, this theorem that actually aims at proving the bijectivity also in the time-dependent case. Assuming we have two initial conditions, the initial condition is the same for the two systems, and some external potential, then the map potential density, well, first of all, is injective. Yeah? So you can recognize if your potential is the right one or not. And then much later, it was Van Leuven who actually tried to explain what was the Hohenberg-Kohn theorem of equivalence of two systems with given an initial condition for one, initial condition for the others, two external potential, two interactive potential. It is possible. If the second one has the Slater determinant representation, it is possible to find a potential that makes the density of the two equal. And now the density is time dependent. Okay, so let me finally write the fantastic equation, the fantastic Kohn Sham equations, because now you see that you have this J, the index of the jth equation. So we have n of these equations. The first part is exactly the same as we expect. I mean, the kinetic part and the external potential, and then there is this coupling. So these equations are coupled by rho, because rho is the sum of all components square, okay? So this is the coupling we have. It remembers a little bit of the Gross-Pitaevsky equation in bosonic case, yeah? So this is squared nonlinearity, no? But this is, here we are talking of fermions, not of bosons. What is the other beautiful thing that you see? Well, the potential, the external potential here is exactly the same external potential of the three n-dimensional Schrödinger equation. So if you design a control function in this picture, you can take this control function and put in your, if you want, in your original quantum picture, and you get the same effect, at least at the level of the density. So in general, you can think that this external potential is made by confining one, something that keeps the electrons together, imagine of the nuclei in the Born-Oppenheimer representation, and a control that you are very well know, a modulating function of time and something depending on space. If this is just x, you have the dipole control. If it is x squared, you have some harmonic control, etc. Yeah? So this is now our problem, to make sense of this, because writing the equation is not enough. We have to prove there is a solution, otherwise it's not a mathematical problem. Yeah? And it surprised me a lot when I tried to find reference on this, that even if this problem is 40 years old, there was essentially no theory available for this system. So let me just, I wrote this small. This means you maybe can, it's not so essential, but you need some functional space, some standard one, like this W space for revolution equations. and some additional space. What I can just point out is that the spaces, and this is essential to prove existence also for the control problem. So this is something that has not been done before. So assumptions are that this correlation potential that we don't know analytically is bounded, is times psi, which makes the Hamiltonian is also continuous real Frechet differentiable, and these are bounded, V0 and V are bounded. Indeed, if you are in a bounded domain, then you can also have x squared, no? But in general, not. If you write the problem in Rn, this is not true, so that would be wrong. There is no solution for the equation in that case, okay? Finally, I put the control. I would like to search it in H1 and not L2 as you usually do, because, well, there are some reason of modeling due to Brocket. This is called minimum tension control, but it is also essential to prove some regularity results. So in L2 will not be possible. At least we were not able to, okay? So let me say, so the first thing is, before you talk about controlling a model, you have to prove that this model has a solution, and giving a control, you get a solution. So it is a injective map, okay? So this is the weak formulation of the Kohn Sham model. So psi is now a vector of psi 1, psi n, and you want that the weak formulation of this model is satisfied almost everywhere in time for all test function h01. Why h01? Because I'm taking a zero boundary condition outside this omega, okay? This is an issue. It means I have an additional confining potential, which is the infinite barrier, no? Infinite wall, as we know from quantum mechanics 1. Okay, so if we assume that the initial condition is in H01, oh, sorry, if it's in L2, which is the lowest possible regularity, then we get a solution H1. So we get, where I wrote somewhere, H1. If it is in H1, then we get H2 regularity in space, which is important for us. And even more, we will need this. If it is in H2, then the initial condition, then psi is in Z, Z will be L infinity to H2. Okay? So the way to prove this result, this theoretical result, is by the standard Galerkin approach, plus some additional functional tools, Karateodori theory, because the control can be bang-bang, and the Aubin-Lyons lemma to prove some compactness of spaces, okay? So we have need some embedding to prove some regularity result. And this is the first part of the work I am presenting to you. So let me make some additional comments, because it is correct to say what has been done and what's not. So first of all, something similar has been done essentially more or less about some years ago by Jérôme, and he could make some similar estimate, but a much more regular setting. Very important, I would like to mention the result by Lebris, Cancès and Lebris about the Hartree potential, which was one of the first to make something like this. So with this regularity of solution of the Schrödinger equation with Hartree potential. Then there are additional results by Baudouin, Cavian, Puel for the Coulomb potential, and they are the main results that we have used also. And we have a problem. The problem is that in some estimates that use the Hard inequality can only work in R3, in 3 dimensions. So as I'm telling you, is not valid in 2 dimensions, yeah? This is an open problem, but you know that the Coulomb potential is in L2 if you are in R3, no? So there is some structural problem if you want to do L2 spaces. Anyway, so let me start the issue of control. Suppose, for example, you have 2 electrons in this potential, which is asymmetric. So there is a lower bump and a higher bump. So the ground state would be in the lowest band. And you want to control these to go, so put the density to go on the other lower bound. Yeah? So how to do this with, say, 2 electrons with some dipole control? This is the issue I'm going to discuss. So optimal control, as you've mentioned many times, means that you want to minimize some functional, just the objective of your control, subject to your model, that is the Kohn Sham equation. Yeah? So it's quite standard. You know all better than me. This is clear. But so what are the possible tasks? One possible task is that you have a desire, no? Like Christmas wish. You want that your density follows some trajectory. So you have some desired rho d, and you want to follow this as good as possible. So minimizing this difference, this tracking part, will do this. Or you want to exclude your density from some region. So you put the characteristic function of this region, and if you want to minimize, means that rho, the support of rho, will go away from that. No? And finally, you want to reduce the cost of your control. So I said I want an H1, so this is the H1. No? So this is very easy to write down. The problem is that if rho is psi square, so this is psi to the power 4, you need that your wave function is an L4. But this is not that standard, because to add this, I need that psi is an H2. So this is why I have very regular initial condition, okay? Maybe for physics, that's essentially. We start always with Gaussian, so it is C infinity. Who cares? But just to tell you, if you take the wrong space, there is no point to make this functional, okay? So this is for beta non-zero. Okay, so let me work with this. So the first point is to prove that there is a control, that we are talking of something which is meaningful. No? So the idea is, can we find a control function H1? I mean, this is by embedding. It means, can we find a continuous function? Okay, no jumps. Can we find a continuous function such that subject to the constraint of the Kohn Sham equation, we minimize this functional here? This is the question. No? And in fact, we can prove this subject to the regularity I told you. In fact, you see, if beta is not 0, I need this higher regularity for the tracking part. Otherwise, I don't need it, so I can put even lower regularity. So there exists a control. We have no uniqueness, but we don't expect uniqueness, no? Especially in quantum mechanics, but we have existence. So we can talk about the control now. And the proof of this theorem, that is part of a second work, is the standard one. You have a minimizing sequence of control in H1. So this is a bounded sequence because the function is coercive. So you have extract a subsequence. And then what is important is by compactness, you have a strong convergence of this sequence, so you have a control function, okay? The Arzelà, this is where I use Rayleigh-Kondrachov. Arzelà-Ascoli is important because if you put a final observation your functional, like the functional, the second one, you see this is a final time. So if you are just in L2, what is in the final time a function? There is no meaning of that, no, of the Lebesgue space. But if it's a continuous function, then you can evaluate the function on that time. And this is why we use Arzelà-Ascoli to prove that actually we have equicontinuity, and so the function is continuous, the limit, yeah, of this control. Okay, so this is the control problem. So we have a control function, and now we would like to get it, to characterize it, no? Because I can only say it exists, but I don't know how it looks like. What is it? Yeah. So the point is to first of all know if you have a uniqueness of solution from control to the state, then you can use a reduced functional. So everything depends on you. It's a reducing functional. And so we have this equivalence. This is our original problem. This is now a global minimization problem in this space. Yeah? C psi u is just the Kohn Sham model, just for short, yeah? Okay? So, characterization means that we can say the derivative of this function is 0. Yes, I lost completely time. But
It's at least 5 minutes talk, but then there are questions.
Okay, okay, I have to speed up. So I have to write the optimality system, which means the derivative of this j in u is 0. And okay, I do be fast. Okay, just one comment. If you do functional analysis with complex Hilbert spaces, it does make sense to make Frechet differentiability as it, because this means analyticity. No, we don't have this. Yeah? This is usually not done. So it is about real differentiability, yeah? Real Frechet differentiability. But real Frechet differentiability means that we still have implicit function theory, whatever we need. And now, since I have only 5 minutes, I skip a little bit. But what is essential is that I'm trying to use the implicit function theory, because I want that the map U, rho U, is differentiable, yeah? And doing it directly is a very difficult task, but using the implicit function theorem, it is much easier. So we needed to prove that all what we have, functional constraints, is all Frechet, real Frechet differentiable. And we do this, okay? So there is some work on this. The functional, the constraint, this is the Frechet differentiability of it. And then, finally, we have Lagrange, Giuseppe Lagrange, no? We have the Lagrange function, must be a real here, because this is a complex function. And by using a famous theorem Borzi-Kursik, we have a characterization. If this Frechet derivative of C is surreactive, then we have existence of a Lagrange multiplier, okay? And in fact, this Lagrange multiplier is in the space X where we have it. Okay, next step is then I can compute the gradient because I want to optimize, but I am in the H1 space. My control function is in H1 space. I cannot use a gradient L2. That will be wrong, because then I have an update. H1 space plus L2 is L2. This is wrong. So I need the gradient in H1, so there is some working to be done. And to compute the gradient, I need to solve the joint equation, which is another equation, completely different. This is again a system. And here we proved also existence of solutions, uniqueness, and so on. Yeah, there's some work done also in this case. Anyway, to make noch faster, okay, I skipped that you need in H1 is clear, that the gradient must be in H1. So now we go to numerics. You want to numerically solve this equation. So you need a very beautiful scheme, which is time invariant, as is a Schrödinger equation, gauge invariant or approximately invariant, and stable, unconditionally stable, it would be even better, non-preserved. And there is one in Fourier space, yeah, so in the pseudo-spectral case, which is done by this one. This has also been analyzed by Mathilde in Innsbruck. Anyway, for the optimization, if you have a gradient, you do whatever method you want. Let's call it grape, but grape is just gradient. But let's say something good for optimization, okay? So you go here and you optimize the problem, and now we are ready to solve it. So let's make a first experiment is just to verify the algorithm. Let's say I give the control U, I construct my trajectory, and then I forget this U and see if I can get it, no? Just verify if it is working. And you see, in fact, as the weight of the control is going down, you get more and more close to the given trajectory, and the functional is going down to some value. So the next experiment is exactly the one I showed you before of two potentials. So I would like to minimize this. This means the density on the left side of the first coordinate must be as small as possible, and we have the control. And all what I'm showing you is, in fact, part of this Cocos Nut code, no? That is published in Computer Physics Communications, and you can download it and maybe play these experiments. This is the second one. So please use it and improve it. So, And this is the result. You see that the density, the initial density, goes through this control function. This is the result of the optimization. You get to the density in this part. And this is the essential part. The fact that you use H1 control is also very important, especially for high-dimensional problem, for optimization. A more regular control space, which means also a smaller control space, is also a way to precondition your method. And in fact, you get a much better result with much less computing time, or you see number of iterations. So please try to use H1 optimization in your schemes. It would be very interesting for you to see the difference. And this work has been done together with Gabriele Ciaramella and Martin Sprengel. Both were PhD students of mine. Now, Gabriele Ciaramella is a junior professor in Germany, and Martin is in the Wetterdienst. So I think now our weather predictions are better than before. And if you want to know more about what has been done more in general on quantum control problem, including results, very interesting results of many other colleagues, just I mentioned Ugo Boscain, who is here, and many others of you. I hope I all mentioned all of you here. So you can have a look at this book of Sam. And I think this is, should be a slide on references. So if you need any information, whatever else, results or questions, I'm very happy to talk to you with you about this. Okay, thank you very much.
Thank you, Alfio, and I'd like to open up for questions.
Thank you. A question and a comment, if I may. The comment first. The story of Runge Groß is not finished, right? I mean, there's still people working on it.
It's completely open.
Yes.
It's completely
Mathieu
open.
living in Paris, for
yes,
instance.
I also said that there are many open issues, many from the mathematical point of view, even a part of the modeling in physics. So I hope they will be discussed more.
My question is about the T.
T, the time?
The time, the horizon that you're using.
Yes.
Did you do any investigation into that?
No, actually not. No, actually not. But we always make some like estimate that the standard approximation by perturbation. I mean that if you have just a change of energies, you have some approximate estimate that we are not much shorter. Or things like this. But this is very rough. Yeah, in this case, T is 1 or 10 or 5. And I cannot really say what physically this means. Yes, yeah.
Picking up on this, indeed, are you concerned about phenomena that have been observed in numerical optimal control algorithm where if the evolution time was not kept long enough, convergence would not happen or there would be traps? But I guess the whole question of the landscape is...
if the control function is not bounded, as in this case, I mean, you can have, the norm can be very high. That is, you can put a lot of energy, a lot of modes in the system, then it is not, this bound on the time is not strict. You can always get very good results. But the energy of your functional can be very, very high, maybe out of your range of, you know. Suppose an infinite control. You get where you want. So.
Infinite time, do you know? Right.
Yeah, I mean,
right,
you put
right,
infinite energy, you want, you get...
no, you
but
can,
essentially is this, no? I mean, if the question...
All to explore. I'm sorry, I'm abusing my role here. Any more questions? Yes, please, yeah.
Yes, thank you for this talk. Do you know if there is some controllability, in fact, results? Because it is a non-linear system.
Yeah.
So even controllability around the stationary things by linearization and something like this. Do you know any results on
no
this kind?
idea, because all what I know about controllability goes does not match with this nonlinear coupled setting. Would be very nice, but I'm really, this is beyond my capabilities. Yeah.
Okay, thank you.
Yeah.
Where is Ugo? Maybe he has something to comment on that. I have a memory about some
No,
controllability
no.
results on nonlinear Schrödinger, but comments, question? I'd like to invite Andra to set
thank you very
herself
much.
up in
Yeah.
the wait.
Yeah.
Time for one more question, and you can come up in the meantime.
Okay.
If not, I'd like to thank Alfio.
Yeah, thank you very
one more
much.
time.
Thanks a lot. Yeah.